stress intensity factor. Why are we discussing this? What is fracture toughness? क्या होता है? आपका क्या बैकग्राउंड है? मैकेनिकल?
हाँ मैकेनिकल।
तो फ्रैक्चर टफनेस के बारे में सुना है?
हाँ।
क्या होता है? What is fracture toughness?
Sir, amount of strain energy absorbed.
नहीं, डेफिनेशन नहीं, या तो यूनिट बता दो। यूनिट ही बता दो।
मेगापास्कल सर।
मेगापास्कल तो स्ट्रेस होता है। So is it a stress? How many types of toughness have you heard of? फ्रैक्चर टफनेस को छोड़ के और कोई टफनेस सुना है?
मॉडुलस ऑफ टफनेस।
मॉड्यूलस ऑफ टफनेस
Rigidity.
हो सकता है, but what does that mean?
Rigidity, that is not toughness.
मॉड्यूलस ऑफ टफनेस पे तो बाद में आएंगे, पहले टफनेस कितने टाइप का होता है? व्हाट इज फ्रैक्चर टफनेस?
फ्रैक्चर होने से पहले जितनी एनर्जी वो स्टोर करे।
सो दैट शुड बी इन टर्म्स ऑफ एनर्जी। क्या पैरामीटर फ्रैक्चर टफनेस का? हाउ डू यू मेजर फ्रैक्चर टफनेस?
जूल पर मीटर mm क्यूब या मीटर क्यूब यही होता है एनर्जी का।
हाँ, एनर्जी होता होगा, दैट इज एनर्जी डेंसिटी व्हिच यू आर सेइंग, जूल पर मीटर क्यूब, एनर्जी पर यूनिट वॉल्यूम, राइट? एनर्जी तो जूल में है ना? बट टफनेस और एनर्जी में क्या डिफरेंस? कोई डिफरेंस है? फ्रैक्चर टफनेस क्या होता है? कितना एनर्जी अब्सॉर्ब किया टूटने के पहले। So why are we studying K? K क्यों पढ़ रहे हैं हम लोग? स्ट्रेस इंटेंसिटी फैक्टर क्यों पढ़ रहे हैं? क्यों डिस्कस कर रहे हैं?
ड्यू टू क्रैक।
Due to crack what? There is a stress intensity.
स्ट्रेस कंसंट्रेशन
It is not a stress concentration. Stress concentration was given by English. Okay. And that is sigma at crack tip is equal to 1 plus 2a by b into sigma applied. This is stress concentration factor, SCF. This is SIF, stress intensity factor. Okay. So why are we studying K?
प्लास्टिक पे रीजन बनता है, प्लास्टिक बोर्ड बनने वाला उसके
ठीक है, बनता है, क्या करेंगे फिर उसको?
उसमें कितना स्ट्रेस होगा मैं उसी को।
प्लास्टिक जोन में तो हमने मान लिया ना कि यील्ड स्ट्रेंथ ही है, तो सिग्मा वाई एस स्ट्रेस है। That's how we derive plastic zone, by assuming that the stress is not increasing beyond sigma ys. So what we will do now with K? What do we do with K? Why have we invested so much time in K? So when on a stress strain diagram, why do we do this? Why do we do tensile testing?
To know the property of material.
Which property?
Yield strength and ultimate tensile strength.
Yield strength and ultimate tensile. What is yield strength?
Sir, after which yielding occurs? Plastic deformation.
After certain amount of strain?
Stress, sir.
Stress. So it's a
स्ट्रेन भी देते हैं हम, स्ट्रेन प्रोवाइड करते हैं टेंसाइल टेस्ट में।
हाँ, कुछ भी प्रोवाइड करो, स्ट्रेस आएगा ना? स्ट्रेन प्रोवाइड करो, स्ट्रेस आएगा। How do you define yield stress?
Stress
Do you define in terms of strain or do you define in terms of stress?
Stress.
सर डिफाइन स्ट्रेस के टर्म में करते हैं, पर इनपुट तो हमारा स्ट्रेन ही होता है। स्ट्रेस
हाँ ठीक है, इनपुट स्ट्रेन होता है, पर मेजर तो स्ट्रेस करते हो ना। If you are defining something in terms of stress, then you must have the value of stress, no? So strain की वैल्यू से तो स्ट्रेस आएगा क्या? नहीं आएगा।
सर इनपुट स्ट्रेन नहीं होता है, इनपुट लोड होता है, जिसकी वजह से इंटरनल रेजिस्टिंग फोर्सेस जनरेट होते हैं। फिर वो
Now you respond to him.
फिर वो स्ट्रेन डेवलप वो वाई एक्सिस पे है, इसका मतलब ये थोड़ी है कि इनपुट है।
बोलो, अभी बोलो, जवाब दो।
स्ट्रेच ही करते हैं सर, उसको स्ट्रेच करते हैं, वो तो इंटरवल
लोड देते हैं जिसकी वजह से इंटरनल रेजिस्टिंग फोर्सेज आते हैं, वो इनपुट हुआ हमारा, फिर वो स्ट्रेन के रूप में हम
Look at him and respond now.
मेरे को इतना ही पता कि हम स्ट्रेन एलिमिनेट करते हैं तो स्ट्रेन हम दे रहे हैं उसके ऊपर, तो उसी वजह से इंटरमोलर फोर्स जनरेट होते हैं उसके अंदर।
How are you saying that? Well, you can be right. I'm not denying that you are wrong.
He's talking about the.
I am saying
Causes
ki if
stress.
you have to pull a piece with your hands, what are you providing? Strain or stress?
इनपुट तो सर स्ट्रेन
Strain दे रहे हो कि stress दे रहे हो?
स्ट्रेन दे रहे हैं।
Stress नहीं दे रहे हो? So your muscles are like this and you're just stretching it like that. ये दोनों एक के बिना exist ही नहीं कर सकता ना? कर सकता है. So then what is the meaning of supplying strain and supplying stress? Or applying strain and applying stress? What is the meaning of that? If I apply strain, can I do that? I am only applying strain and I am not applying stress. Can I do that? ऐसा कोई strain apply कर सकते हैं जिसमें stress apply ही नहीं करना पड़े? हाँ? कर सकते हैं. How will you apply strain? I have piece of object and then I'm saying that I'm applying strain and not stress. So that means I'm creating some amount of delta L. In order to do that, I need some force, no? Strain कैसे लगाऊंगा मैं?
परफेक्ट प्लास्टिक के
2 मिलीमीटर खींचना है, 1 मिलीमीटर खींचना है, बिना फोर्स के कैसे खींचूंगा? हाँ? ऐसा हो सकता है कि स्ट्रेन लगाए स्ट्रेस नहीं लगाए? हो सकता है?
टेम्परेचर इंक्रीज से होता है।
टेम्परेचर इंक्रीज से थर्मल स्ट्रेन आएगा.
उस केस में
हाँ, उसमें स्ट्रेस होगा. But yes, that is correct. But there we will not get yield strength. We will get a constant strain without stress. So what will be measuring? We will be measuring coefficient of thermal expansion. Alpha measure करेंगे, है ना? Deformation होगा उसमें? होगा?
less change of the deformation.
Really? You should think about it. क्या होगा? Thermal strain में
shear नहीं ना होगा।
क्यों नहीं होगा shear? चलो shear नहीं होगा. Deformation होगा कि नहीं? Dislocation will move or not? बोलो. Temperature increase किया, क्या होगा? Force नहीं है. There is no force. So I'm increasing temperature. The object is expanding. So what is happening? Dislocations are moving there. Saurabh?
No sir.
They're not?
ऐसा नहीं होगा.
Why?
सर सर यहाँ पे स्ट्रेन थर्मल एक्सपेंशन की वजह से आ रहा है सर.
हाँ, आ रहा है.
Yes,
पर strain तो आ रहा है ना?
yes sir.
तो dislocation move नहीं करेगा तो strain कैसे आ रहा है?
So molecules will expand, but they will not.
Molecules will expand.
मतलब
कौन सा molecule?
Spacing. Intermolecular spacing.
Intermolecular spacing.
Yes sir.
Talk in terms of metallic materials, if you can. ठीक है, polymer में ऐसा हो सकता है. Polymer में बहुत कुछ हो सकता है. Metallic materials में, what is the molecule? In steel, what molecule you have? Which molecule do you have in steel?
grains.
Grains are molecules. तुम क्या molecule है steel में? क्या अरे क्या?
Atoms होंगे उसमें।
Atoms, कौन से atoms हैं?
Iron के
Iron atom.
carbon atoms होंगे।
So is there a molecule?
No, sir.
No. Good. So there are atoms. So interatomic spaces means lattice parameter. That will change.
Yes.
So dislocation will move or not? Oh God.
Atoms will expand, but the dislocation will not.
Yes, they will not move. They will not move. And the first hint is you remove the temperature and it will come back to its original place. So it's not permanent. Right? So dislocations are not moving. Forget clear, na? Okay? There are other arguments. For moving dislocation, you need stress. Pearl and barrow stress is needed. You have no stress, so it can't move. Okay? So when you think that I'm applying strain, we don't call it strain applied or displacement applied or force applied test. We call it displacement controlled or force controlled tests. There are two types of tests which you can do. One is displacement controlled. and another is force control. You can't stop another force. You can't just apply displacement without application of force and vice versa. You can't do that. Thermal is one example, but there is nothing happening there. Okay. So displacement controlled meaning you want to control that within a second you are only going to stretch 2 millimeters. This is what you are controlling. When you are doing force control, then you are saying that I will apply 20 megapascal in 1 second. This is what you are controlling. Okay, you can't stop strain there or in the other scenario stress. So we have again come back to basics, very basics. Well, so now this is, if it is understood, then in a tensile test we get this kind of curve. We don't really get this, we get force and displacement, we convert that to stress and strain, and then why are we doing this? After 10 lectures I'm asking these, why are we doing this? Why do we do tensile test? Young's modulus के लिए tensile test नहीं करता है. अभी तो आप कहीं नहीं पहुंचे हो फिर इसका मतलब. So let us talk now about this. Now is becoming a tutorial session. So when you are doing, you should do a tensile test. Have you done it? You must do. अभी आगे फिर करो. कॉलेज में बीटेक में किया था कि एमटेक में किया था? बीटेक में किया था.
एमटेक तो कर ही रहा है.
बीटेक में तो कोई करता नहीं कुछ. हाँ, so you watched it, no? Or did you do it? So you put it in the machine and started the machine and you just watched it, witnessed it. So you should do it again. Hopefully our UTM will work in this
last of this month.
incarnation of mine. If that happens, then we should do it. Okay. So we are going to, whatever test we do, conventional test for which standards have been made. Okay, so experiment and test, these are two different things. Experimentation means, so experiment word can be used in English literature also. Like, why are you experimenting with this? If I give you a sophisticated thing and then you are just tinkering with it, then I might tell you that why are you experimenting with this? What does that mean? You're not really doing any standard test. Experimentation means you are trying something out.
Results are not definite.
Results are also not defined. You are also not sure of the method which you want to apply. You might have some idea what do you want to measure or what do you want to see. Sometimes you might not have. Like for example, you just take a piece of metal and look it at under transmission electron microscope. You really have no idea what you want to do. You are just looking at it. So you are experimenting with it. You are playing with it, tinkering with it. Right? So when Heisenberg designed an experiment to prove whether quantum really exists or not, that example of Heisenberg's cat, which is dead or alive inside a box, that is an example of experimentation. Experiment also to disprove whether ether exists in the universe. There was an idea, no, that there is a fluid in the universe and all the planets and celestial bodies are floating in that, and that fluid was ether. Okay, so somebody said there is no ether, there is nothing there. So how do you prove it? It's just a theory if you can't prove it. If you can prove it mathematically, it's a theory. If you can't prove it mathematically also, it's a hypothesis. If you can prove it experimentally, then the goal is done. Unless somebody else does another experiment and disproves that. Okay, so Michelson's and Morley, they designed an experiment to disprove ether. Those are experiment. Tests are something where you know what to do, you have a standard method to measure something and you apply that to find out certain properties. For example, if you want to find out density of an object which is irregular in shape, so you apply Archimedes' principle, put it in a liquid, replace the displaced liquid, measure that, and then you get the density, apparent density of that. That is a test. So finding out the property under tension is tensile test. and there are standards for that. So there are well written documentation where it is mentioned that how should you design the specimen, what should be the shape of the specimen, in which way you should conduct the test, how should be the fixtures, and all those things are written. And then it is also written that how do you calculate stress and strain, and how do you find out yield strength, and how do you find out UTS and percentage elongation and reduction in area, uniform strain, all those things, but not Young's modulus. Why? Why can you not measure Young's modulus from tensile test?
It is not directly measured, but we calculate from that slope of the.
Yeah, but that will be wrong and not minutely. So if your steel sample has a Young's modulus of 200 gigapascal, then the slope which you will be calculating from your stress strain curve in a tensile test will only be somewhere around 20 gigapascal. So 20% of the real value, 10 to 20% of the real value you will get. Okay, you will never get 200. Why? So you should do, all of you should do a tensile test. And you should measure the elastic modulus. Why will you not get 200 gigapascal or the real value of Young's modulus?
सर वो इलास्टिक रीजन में स्लोप से फाइंड करते हैं ना.
हाँ, इलास्टिक रीजन में क्यों गलत आ रहा है एक्सपेरिमेंट में?
Sir, Young's modulus keeps redefining, sir. Means, sir, when it goes in plastic zone, value of Young's modulus keeps rechanging.
Yeah, but we are measuring the slope in the elastic region before yield strength. Then why am I getting such a low value? We can measure it from tensile test if you use extensometer. If you don't use extensometer and you are getting the displacement from the machine, also force from the load cell, force anyways you will be getting from the load cell only. But displacement you can measure from the actuator of the machine. So there is a grip, and that grip is being pulled by the UTM machine, and UTM knows how much its frame is moving. So that is called crosshead speed, and from crosshead speed into time you get the displacement, and that displacement is given to you by the machine. Okay, so if you use that displacement to calculate strain, you will not get the Young's modulus correctly. Why?
Because that upper portion will also deform, and that machine will give the reading along with the whole specimen. But we are taking the reading of only that gauge length, so we need to provide extensometer.
Yes. So now you remember. So the total strain which you are getting is the strain which you are getting in the specimen and the strain which you are getting in the grips and fixtures. Hardly the UTM overall fixture really doesn't matter that much as the grips, they matter, because the dimensions of grips are smaller in comparison to the machine. So if you are applying 200 megapascals, that same amount of force, not stress, is also applied on the fixtures, right? Fixtures are also under the tension load. And why do we have this dumbbell shape of tensile specimen? ऐसा shape लेते हैं tensile specimen का, क्यों? Dog bone shape. Why do we test like this? So the specimens looks like this. If you have done in BTech. वो rod थी, वो pure rod थी, उसमें कोई shape नहीं था same. So then you have not done it. You have not done it properly. हाँ, इंडस्ट्री में ऐसा कर देता है. कहाँ से टूटा हुआ स्पेसिमेन?
मतलब लेंथ ये लेंथ लेते थे, तो मतलब ऊपर की तरफ था. पहले मतलब एलोंगेट हुआ थोड़ा सा. स्पीड से हम लोग रॉकेट टूटा था।
टूटा कहाँ से?
ऊपर से मतलब
ऊपर से टूटा ना?
हाँ।
So keeping that in mind, now you tell me why do we have this kind of shape?
हम चाहते हैं सर कि वहाँ से टूटे बीच से, इसलिए
तो उसके लिए कम क्यों किया हमने?
Concentration.
ऐसा क्यों बनाया?
स्ट्रेस कंसंट्रेशन ज़्यादा हो जाएगा सर,
स्ट्रेस कॉन्सेंट्रेशन ज्यादा नहीं होगा, स्ट्रेस ज्यादा होगा,
स्ट्रेस ज़्यादा।
because stress is forced by area. So you are decreasing area here. So for the same amount of force, always the stress will be higher on the smaller area, right? So whatever happens, all the material points in whole of the fixture, UTM and specimen will be following their own stress strain diagram, whatever material they are made up of. Okay? So because the diameter of the sample is smallest in the whole assembly, the stresses will always be higher, so they will always be ahead in their stress strain diagram. Okay? So elastic region will come earlier in them, plasticity will begin earlier in this, damage will begin earlier in this, they will fail earlier than adapters and other things. If your adapter has a stress strain equal to this, that should be the worst condition. You can have a worst condition, that you have even softer adapters which have a stress strain profile which is something like this. So if you make a polymer का fixture बनाया और उसमें metal का sample डाल के load कर दिया, तो sample के पहले fixture टूट जाएगा. Okay. So worst condition could be that you are making an adapter which has exactly, so it's the same material of the tensile specimen, you are using the fixture also of the same material. Even then, the sample will break first and fixture will not break first, because the diameter of this section and beyond, ये part जाएगा fixture में, तो fixture का diameter जो है is going to be larger than this, so the stresses are going to be less in the adapter, in the fixture. Okay? And the strain, but all of them will be elastically deforming. They will be elastically deforming. Once it breaks, they will recover. So fixtures are good to go for the next time also. But while the test, they have deformed elastically, right? So the strain which you are getting from the machine also includes the strain which is coming because of the elastic deformation in the grips and fixtures. Okay?
इसीलिए गलत होता है।
So because you have larger strain in comparison to what you should have, it means that material deformation which you are getting is showing more strain in comparison to what you should have. Okay, so it means that the material is a little softer looking on the curve, not really it is, because you are getting this extra strain from the machine. So your Young's modulus will go down, your slope will go down. Okay, so this is called machine compliance. You should read about this. And how do you remove the effect of machine compliance? If you use extensometer, extensometer is an instrument which sticks to the sample, and you should remove it as soon as the curve changes its slope. As soon as you are in the plastic region, you should remove it for the safety of the instrument, because then necking will happen. After some time, necking will happen. You don't know how much time it will take for necking, so you should remove extensometer. And extensometer is valid only for elastic region, because once it deforms locally, you have necking, then extensometer might not go in that area, so you will be measuring the strain somewhere else. As long as the strain is uniform everywhere, which is in the elastic region, extensometer, so extensometer is just measuring how much change in diameter is happening. Okay, so if the diameter is going down, then the two tentacles of extensometer will come closer. This will give a change in the resistance, and the change in resistance will be calculated via a Wheatstone bridge, where you have an unknown resistance and 3 known resistance. That signal will be converted back to strain, which you will be getting in your machine.
लंबा से जो लगाते हैं उसको क्या बोलते हैं?
Yes,
वो एक्सटेंसोमीटर होता है,
बीच में
बहुत सारी चीजें लंबी होती हैं, जैसे COD गेज भी लंबा.
वो यूज नहीं होता।
So if you have a cracked specimen, then you put similar device here, okay, and this device is measuring how much opening is happening
Load landed.
at the crack tip, okay, and this also works on the same principle, but this is not extensometer, okay, but well, the device instrumentation is same. In this case it is going to open up, in tension it is going to get closed, okay. So coming back to the same question, tensile test we do to measure yield strength and all those things. Okay, so now let me ask another question. Why are we interested in finding out yield strength? Why do we want to know what is the yield strength of material? क्यों जानना है?
To avoid the material failures.
परमानेंट डिफॉर्मेशन उसके बाद होगा सर yield strength के बाद.
हाँ, but दूसरा the sample which we are testing, we are not going to use that sample in making the bridge, no? We'll be using the same material but different, not that exact sample, right? So how that yield strength which we have obtained from that tensile sample is going to help in formation of a component, a bridge, a pillar or a vessel or whatever, same material. ले लिया factor of safety, but the yield strength which you are getting from a specimen of the same material which you have tested in lab, how that is reflecting the yield property of the same material in the component.
So grain boundaries देखते हैं
No.
सर वो तो कंबाइंड लोडिंग का केस होगा फिर थ्योरी ऑफ
No,
फेल्योर.
don't go that complicated. I just want you to tell me this, that because they are same material, they are going to have same yield strength. You should say this. Say it now. Do you believe in this?
Yes.
Yeah? Same material, same yield strength. And what do we call it? We call it material property. So yield strength is a material property, resistivity is a material property, density is a material property. What about fracture toughness?
material property.
प्रॉपर्टी
Just property.
मटेरियल
So cracks also discontinuities in the material.
है, वो तो टेंशन टेस्ट में भी है ना डिस्कंटिन्यूटी. फ्रैक्चर टफनेस मटेरियल प्रॉपर्टी है. How do you define a material property?
So जो depend ना करे material.
Why do exactly?
Quantity पर depend है जो
जो क्वांटिटी पे डिपेंड है वो मटेरियल का अपना प्रॉपर्टी है, राइट? चाहे बड़ा हो चाहे छोटा हो, डेंसिटी सेम हो, लैटिस पैरामीटर सेम हो, unless you change the temperature. So optical property, electronic property, there are a lot of material properties which do not change unless you bring a lot of. So for example, gold will not change its color unless you make it nano size. Then it changes its optical property. Okay? So steels are going to have same Young's modulus. If you are changing the temperature, Young's modulus changes. Okay? Marginally it changes, yield strength will also change, UTS will also change. Okay? All these things will change, but at the same temperature, they are materials property, and that's why we can use these properties for design criteria. है ना? अगर ये बॉडी टेम्परेचर होता फिर तो सैंपल का अलग आता, कंपोनेंट का अलग आता. Okay, so what about fracture toughness? So first let me describe what fracture toughness is. So in a tension or compression test, you increase the force or displacement, whatever, and then the stress increases in the material, and then it changes its slope, okay, and then via 0.2%, or if there is sharp yielding, you find out one point beyond which the material is going to deform permanently. That's a material property. So it's a critical value of stress beyond which if you go, the material will not come back, recover completely. It's a critical value of stress. Similarly, in a cracked body, if you keep on increasing stress or force or displacement, in whatever terms you are applying the force on the system, the load on the system, then K is also going to increase. Okay? And K is something which is unique in definition of all the stresses which are there in presence of a crack, sigma xx, sigma yy, sigma zz, all of them has k in it. The other functions are dependent on theta and r. So if you want to find out the stress here, then you know that this is your r, this is your theta. If you know k, you can calculate all the stresses. Okay, so k is something unique. K factor alone can describe the stresses. Is it okay? So when you increase stress, then k is also going to increase. A can also increase. With increase in stress, crack can start propagating, right? And that will be compensated in stress intensity factor. Of course, you will have f of A by W, but once you know A, then the K will also be known, right? So after a point of critical K, you can define that if you begin with a crack length of A, you can define, so you are now loading, and then again in this kind of testing also you get force versus displacement. Okay, and from this force versus displacement you have to calculate the value of stress intensity factor. Okay, so with this increment you can also plot K, which is increasing with delta, and beyond a value of K, crack starts propagating. If you are having a stress condition or crack condition so that the K is smaller than that critical value, then crack will not propagate in that material. Okay, so if I take a ASI 3040 steel, mild steel, titanium alloy, all of them, this critical value is going to be same. If you cross this value, crack will propagate and you can't stop it. And if you are lower than this value, crack will not propagate. Okay, so this can help in design criteria. How? So from manufacturing, if you make a component, we know by doing ultrasonic testing that what is the maximum size of the defect I have, right? What are the cracks which have been created during the manufacturing process, for example, because of shrinking in ingot casting. Okay, so I know the worst condition, that this is the maximum size of crack I have. For that I can calculate what will be the stress intensity factor for worst condition. And what is the worst condition? Mode 1. Mode 1 will give you highest value of stress intensity for the same amount of stress if you load a specimen in mode 1, in mode 2 or in mode 3. If you apply same amount of stress, K will be maximum in mode 1. Okay, so if you are good for worst case, then obviously you are good for the other better cases, right? So this is why you do testing in mode 1 unless you are really interested to understand what is happening in different modes. Just for design sake, people do mode 1 fracture toughness testing. Okay? So when you do mode 1 testing, then you are increasing slowly the value of stresses, and thereby you are increasing the value of stress intensity factor for the known amount of crack. Or you can know from the test that for, let's say, titanium alloy, some alloy, you are getting a critical value Kc or K1c, I will call it, because I am doing the test in mode 1. If I just write Kc, I do not know in which mode the test was done. Okay, so this is written in Roman because all these studies started from, not from Rome, from physicists. Okay, and you will see the earlier studies, they use a lot of temperature. So when they use temperature in calculation, you will see the unit to be Kelvin. So physicists, their favorite unit is Kelvin for temperature. But then when fracture mechanics came to fracture mechanics guys, engineers, then it changed to degrees Celsius, and this unit conversion usually goes on. I don't know how politically influenced is this, but it changes once in a blue moon. So for example, in the state of California for a very long time they were following their own system, which is SI units, and then suddenly they changed to British system, imperial system. So they went back to foot and pounds and all those things. And who knows, they might have come back to SI units, I'm not so sure of it. So for, why was I discussing units?
Temperature.
Fracture toughness.
Fracture?
The viewer-
Kelvin.
Okay, so I have forgotten.
K1c.
So
One
mode 1 is the worst condition, and in that condition for a crack length, if you are doing for this alloy, you do the testing and you can find out when the crack started propagating, and that value is K1c. Okay, so if I have K1c, somebody has done the test and told me that this is the value of K1c. So let us say 180 MPa root meter. Okay, MPa root meter is the unit of K1c. It is coming because of MPa root meter. Okay, so if this is the value of K1c, I can find out that how large of a crack I can accommodate in my component. Okay, so from this I know that this must be equal to sigma root over pi AC. That's the value of critical crack I can have in my system. Okay, and if I have a pressure vessel which is internally loaded by pressure, then if I take a small element on the outer radius of the material, okay, and suppose I have a crack like this, so I can imagine that to be something like that, where this is going to expand, so this is going to bend because of pressure, a small element of that. Okay, so this is going to be in mode 1. Even if it is not, so the crack can be a little tilted, but worst condition will be mode 1, right? So that takes care of the factor of safety there. Okay, so from this I can calculate, so f of a by w I know for mode 1. Okay, and then I should know how much hoop stress is there in that pressure vessel. From that I know what is my operational stress condition. Okay, so I plug that factor there, I know this value, I know that value, pi everyone knows, so I can calculate AC. And suppose AC comes out to be 5 millimeter. So then I know that no crack in my system should be larger than 5 millimeter. And then I do ultrasonic and see that maximum amount of crack which I am getting is 3 millimeter. Then I will take that plate or sheet or whatever it is, and if it is 6 millimeter, 5.5 millimeter, I will not take. I will reject. Understood the importance of K1c? Yeah. So this K1c appears to be a material property, at least a design criteria for sure. But there is a size effect. And before we go in that size effect, well, now we are talking about it, so I'll finish it. So if you calculate K1c for the same alloy, so let us take titanium alloy, and I do the testing for a very thin sample, and I keep on increasing the thickness of the sample for a very thin sample to a very thick sample. So what am I changing? Plane stress to plane strain. Okay, and if I plot it, then initial region is unknown, and then it shows this kind of profile. It is not K, it is K1c. So for different thickness value, you have done the fracture toughness testing and you have found out the critical K value for which the crack starts propagating. That value you are plotting. Do you understand? No? नहीं? हाँ नहीं, कुछ तो बोलो. नहीं समझ रहे हो? नहीं समझ रहे हो? क्या नहीं समझ रहे हो? So let us take this point. This point would mean 2 millimeter. What is my x-axis? My x-axis is thickness of the specimen. Okay. So when I tested a specimen which had a thickness of 2 millimeters, so far in our derivation we have not looked in the third dimension. We have not looked in the thickness direction, right? So if my specimen thickness was 2 millimeter and all other dimensions will scale according to thickness and crack length as per standard, okay? So usually you use this kind of specimen. I'll discuss this in detail later, how to do the test. So, well, this is known as the width of the specimen, which is usually 2 times of the thickness of the specimen, and this, and this is the crack tip, and this distance is called crack length of the specimen, not from here, from there. Why? Because that will be aligned in the testing machine, okay? So you will have pins here, and these pins will be connected with the machine, and the machine will be pulling this pin up, and this pin will remain fixed. Okay, so it is like tension test only with pins. Instead you have a plate which has a crack in it. Okay, so this is the kind of specimen which you test. Another kind of specimens are also there. This is called compact tension specimen. So if you change the thickness, other dimensions will also change, so that it becomes geometry independent. Okay. So if I test a specimen of 2 millimeter and I find out that what is the critical value of K beyond which crack starts propagating, that value is this. Do you understand now? Really? क्या नहीं समझ में आ रहा तो बताओ मुझे.
सर थिकनेस का इफेक्ट कैसे सर क्रैक लैंप?
वहां पे तो हम बाद में आएंगे, पहले तो ये समझ लो जो प्लॉट कर रहा हूँ वो समझ में आ रहा है. I am telling you the fact that as I increase thickness, this changes. I will tell you why it changes. But for now, do you understand this curve? What am I plotting?
थिकनेस इंक्रीज हो रही तो कम डिक्रीज हो रहा है.
हाँ, decrease हो रहा है फिर constant हो रहा है. Okay? So I told you in plane stress plastic zone is more. If the thickness of the specimen is less, it is near to a plane stress condition. And I will come to that and will prove you that in plane stress plastic zone is larger. Okay, I don't have time today. I wanted to do that. I will do that without explaining what it is, and that I'll explain in the next class. But because now you have asked me, so let me show it to you. इसका वायर किधर है? प्रोजेक्टर ऑन है?
Honest. Then
So do you see? Yeah. You see. Okay. So when we take plane, so forget about this curve. That we'll discuss later. So von Mises criteria is sigma 1 minus sigma 2 whole square and summation of all other principal stresses differences of that, right? Square root of that. So this is equal to that if it is a uniaxial condition and sigma 1 is giving you sigma yy, which is a principal stress. If that happens, then all others, so sigma 2 will become 0, sigma 3 will become 0. Okay?
square.
So what will you have? Sigma 1 square, 2 sigma 1 square will be equal to 2 sigma ys square, so sigma 1 is equal to sigma ys. Right?
Square छूट गया.
कहाँ छूट गया?
Second term.
अरे ठीक है. So this is von Mises, okay? And sigma 1, sigma 2 from our Irwin's derivation is k by 2 pi r cos theta by 2 1 plus sine theta by 2, and this is 2 pi r cos theta by 2 1 minus sine theta by 2, And if it is plane strain condition, then sigma 3 will be mu into sigma 1 plus sigma 2. And if it is plane stress, then this will be 0. Understood? Now you plug the values of this in this equation. So you will have a function of r and theta equal to sigma ys. Sigma 1 is being replaced by a function of r and theta. 2 r and theta. 3 r and theta and mu. Okay? So you have on the left hand side something which has r and theta, and on the right hand side you have a constant value which is a material property which is telling you that plasticity has begun. So you find out the value of r for which plasticity has begun, so you can calculate the value of Rp, plastic zone. Okay? So if you assume plane strain, then you will use this and you will put that here. If you assume plane stress, then you will not use this and you will have a different expression, right? And by doing that, internet nahi hai. So, you have to do this. You have to calculate the value of R by plugging these things in. You have to calculate the value of R. This is a personal assignment to you. Okay? And all of you have to write a code on this. Okay? That is not very, you don't really need to write a code. You can do it in Excel also. So what will you have? You will have a function of r and theta is equal to this, right? So then you can find out r is equal to some function of theta into sigma ys, and also mu will be there. Okay, so function of theta and mu. I shouldn't call function, those are constant values. Theta will be changing, theta will be a variable, and you will get different r values. This r value is defining when plasticity has occurred, right? Because we are using von Mises criteria. Okay. So for different values of theta in Excel, you can have theta going from 0 to whatever. You can calculate r value going from whatever, and then you plot r versus x, or normalize r versus x. So that's what I have done for you guys. Do you see here? So some arbitrary value of k and sigma y, and then theta is varying from 0 to 360, you can vary, and then you calculate the value of plastic zone radius for plane stress condition and for plane strain condition, and then you plot it. And the red one, and you might not believe me, might not believe me, so that's why I'm showing you that. So you see x and r. So r here is for plane strain, okay, and rps is r for plane stress. So you'll get two different expressions because sigma 3 will be different. Okay, so then r is plotted for plane strain, it is plotted with a dashed line. So that is the dashed line. This is the dashed line, and this is the tip of the graph. नहीं समझ में आ रहा है? Y axis पे R है, X axis पे X coordinate है, okay? And this R is normalized, but forget about that. And then the radius for plastic zone for plane stress condition is in the red symbol with a line, okay? So that's the red line, है ना? So ये zone है plastic deformation का for plane stress, ये zone है plastic deformation का for plane strain, okay? So for plane stress condition you have, that means larger plasticity. What does that mean? A softer material. It feels like same alloy. If the thickness is less, it acts softer. Why it is happening? Same alloy, same material को change नहीं किया. एक पतला है, एक मोटा है. No magic is happening just because of the calculation. And in that calculation, nowhere I have assumed anything but plane stress and plane strain. What does that mean? Sigma z in one case is 0 and in another case it is not. What is sigma z? It's the stress in the direction of thickness. If that stress is not there, then material is free to flow in the thickness direction. If that stress is there, then that stress is obstructing that movement, causing a strain, causing constraint to come. Do you follow? एक रुकावट है, थिकनेस डायरेक्शन में स्ट्रेस होने की वजह से एक रुकावट है मटेरियल का फ्लो। मटेरियल जाना चाहता है, बट वो तभी जा सकता है जब वो स्ट्रेस को क्रॉस करे। उसके ऊपर जो स्ट्रेस लग रहा है वो सिग्मा 3 भी लग रहा है उसको। ओके, so there is an obstruction in material flow. That's why plastic deformation is not that easy when the sample is thicker. Okay, so that's why you get that difference, that fracture toughness for thicker specimen of the same material is smaller, and after a certain value of thickness it becomes constant, and only in that range it's a material property, because material property should not change with thickness. So beyond that thickness of plane strain, K1c becomes a material property. So the K1c which you calculate as a material property must be plane strain fracture toughness. You must ensure the condition of plane strain. Under plane stress, it becomes a game of individual component. Okay, so there you can't use whatever you have measured from the lab specimen, that thickness and pressure vessel thickness, if they are different, you can't design it based on your lab value of K1c if it is not in plane strain condition. Understood? Okay, and last remark is, if you go in plane stress condition, it increases, but there is a region beyond which, if you decrease the thickness further, people have different opinions and experimental values for this region. Some people find a constant value where it doesn't change. Some people find a decreasing value of fracture toughness, and those things are not known. This region is LEFM, where plastic zone is significantly smaller and you can ensure plane strain condition. In this region, it is elastic plastic fracture mechanics, where plasticity is significant. K1c is not so much valid there. You can still measure it, but that will be plane stress condition, or somewhere in between plane stress, plane strain condition. And this region is called as general yielding fracture mechanics, GYFM, which is the case for thin sheets. And we close the session today.